ladies and gentlemen, come one, come all, welcome to the 2022 Electromagnetic Universe World Expo. Today we have our guest, Robert Ashcroft. Robert Ashcroft has a Bachelor of Applied Science, Computer Science, various fields in computing as a career culminating in data architect for Australian government agency. Primarily involved in documenting data standards and business modeling for development of automated systems. Now semi-retired, examining basics physics from 2014 and examining the fundamental basic building blocks to produce our universe.
My name's Robert Ashcroft, and I'm going to do a presentation about the Millikan experiment that was conducted in the year 1908 through to 1909, with the publication of the results in 1910. At the time, atomic structure wasn't worked out, and all that they knew at that stage was that there was a thing called an electron. They didn't know about the proton, they didn't know about the neutron structure. So what I'm doing is reviewing Millikan's experiment and asking the question, did Millikan actually record or determine the charge of an electron and the charge of a proton? And at the end of this presentation, hopefully you will realize that Millikan made a mistake, and it was a mistake in assumptions. So I'll just swap the share screen. I'll turn on my share screen and I'll show you the timeline of things that occurred around the time of Millikan's experiment. At the time, they knew that there were atoms, they knew there was photons, they knew that there was electrons. However, they had yet to find the proton, they had yet to find the neutron, they had yet to find the neutrino. Antimatter wasn't known generally. However, it was actually referenced or surmised in around by 1898. And the isotopes, the variation in chemical elements was not known. So the guys set up an experiment, and there were two people involved in trying to determine the charge of an electron. One was an American named Robert Millikan. He had a team, and his collaborator was an African American. In Austria at the same time, there was an experimentalist called Ashcroft, and he did similar experiments, except he used water drops rather than oil drops. And at the time Millikan published his results, Ashcroft criticized quite severely Millikan, and it caused a bit of an argument, a serious argument that was never really resolved. What Ashcroft established was that the electron had a fractal charge, and Millikan did not establish that. And the argument about how accurate his results were, Millikan's results were, is debatable. And when his laboratory books became available, it was clear that he chose the good data and didn't publish all the data, whereas Ashcroft, being the traditional experimentalist, published the warts and the good. So what did the experiment from Millikan's point of view look like? It's as is described here. We have an atomizer with a source of oil in it, and it was a perfume bottle sprayed into an evacuated chamber. It wasn't perfectly evacuated, but close. The oil drops then fell through a metal grate where it gathered charge, and that was set up by polarity. A battery was applied to it, and negative to one side and positive to the plate below. And then it fell through into a chamber where you had a graduated microscope and a light source. And this experiment is very, very difficult to do. I did it when I was doing university some 40 years ago, And it didn't take much to muck it up. And it was quite a hard experiment to do. So what was happening is, I'll just leave the share screen, the thing there, and I'll turn off my share screen. So what Millikan was doing was to try and determine the charge value. And the process was an oil drop. It's traveling through the charge grid, and it attracts electrons, and they deposit on the oil drop. And then using the electric field of the two plates, the above plate and the bottom plate, you get the oil drop suspended in air. And you're trying to make the oil drop sit there while you look at it. So you're looking at the oil drop and you're trying to keep it very close. You do a measure of its diameter, determine its density, and then work out what the voltage level is required above to force the oil drop to hover against the fall of gravity. When you do this many times, you get an aggregate data set, and the charges will not always be, 1 electron per oil drop or minus 1 electron per oil drop. So this experiment's well documented. You can search YouTube or Wikipedia and read all about it. But there was a mistake, and the mistake was what the oil drop acquired was negative charge through the electrons, or it lost negative charge through the electrons. And when I was thinking about this, having a shower one morning, I thought, oh, there's a mistake. They never measured the value of the positive charge due to the proton. And the reason why that didn't occur is because protons do not jump from the grid to the oil drop. You need a chemical reaction to achieve that. So what they measured was the presence of excess electrons or the absence of electrons. So when you've got excess electrons, you're going to get a negative charge, and you'll be able to determine the negative voltage values and all the rest of it. But when you take electrons away, you get the positive value of no electrons, missing electrons. You don't get the value of a proton. So I was engaged with a research group in the United States at the time, and I made the comment to the group that the positive charge for the proton, its value had never been determined, and suggested a method by which you could measure that charge. And the charge requires one of two things. You either get a hydrogen atom and ionize it and look at electrons and protons. Very difficult to do. So you need to be able to look at the electric and fields of the protons and the electrons and track them. The other alternative is to watch neutrons in decay. And neutrons in decay will produce electrons and protons. And if you watch those in a cloud chamber and observe spin and a few other bits and pieces, you will get the dynamics of that process. And if you do that, you'll actually be able to measure the value of the electric charge for the negative particle, the electron, and the electric charge for the proton, which will be positive. And it was my claim that the values of the electric charge due to the electron and the electric charge due to the proton were not equal. And the reason why I'm saying that was the case is because the mass value of the proton is 1,836 times approximately more massive than the electron. So the charge values cannot be the same, because if the charge values were the same, the electron and proton would be the same size. The further wrinkle is after 1910 and after a lot more experimentations, and when nuclear physics came along, they found out that there were multiple types of electrons. There was a light, medium, and a heavy version. The same was true for the protons. There was a light, heavy, and medium version. And those particles, the electron and proton, came with an opposite charge configuration, which had 3 varieties. So when we talk about the value of an electron charge, there are actually 3 separate values. And for the proton, there are 3 separate values. And for their anti-charged particles, equivalents, you'll get the same result. So the implications of this are quite serious. All the textbooks that quote the charge of a proton are wrong. The mathematics that assumes these values will produce incorrect results. And as a result, not everything in experiments will work the way you're expecting it to. So, having made the prediction that these values were different, and the team in the United States having a lot more money available to them than I did and the equipment required, did the experiment. And the hearsay response I got from the group was that, yes, the electron charge and the proton charge values were different. But the difference between the two is the proton plus the value golden ratio divide 2, add those two together and you get the electron charge. And the question I have is, why is it phi on 2, the golden ratio on 2? And the answer is the electron and proton have to be a construction. And the construction is interesting in the sense that the monopole charge we observe is showing one face of the dipole, the electric dipole. And the other face of the electric dipole is inside the construction. And the reason why I can say that is if I have an electric negative charge in this hand and an electric negative charge in this hand, and I counter-rotate them like so, those charges will attract because the electric fields will cancel out. However, if my 2 electrons are rotating in the same direction, they will repel. And in the case of the proton and the electron, if they're rotating in the same direction, they attract. If they're rotating against each other in counter-rotation arrangement, they will expand, they will separate. And these are fundamental rules inside electromagnetics. If we go back and check our data, we'll find that that's true. But the interesting thing that they discovered in 1940s was that the electron and the proton have a dipole magnetic field, north up the top and south down the bottom with a charge in the middle, monopole. And that occurs for the electron, it occurs for the proton, and in the case of the neutron, you get 2 sets of magnetic dipoles and 2 sets of electric charge because there's an electron and there's a proton involved. And these 2 configure, so it's a multipolar structure. And to balance it all out, to make the neutrons stable, we need to pull in neutrinos. And I am claiming that a neutrino is a higher frequency photon, which is also being confirmed. The end result of all of this is our understanding in electromagnetics needs review. And we've got to go back and examine these old experiments and see, given the information that was known at the time, is the experiment still valid subsequent discovery? And in the case of the oil drop experiment, we can clearly show that it, A, did not ever measure the value of proton, and B, it, because of assumptions, produced a false result that is now embedded in our understanding in electrodynamics, and it's wrong. We need to fix it.
Well, there you have it, folks. Thank you for being here for the 2022 Electromagnetic Universe World Expo. See you on the next round with the next presenter.